Perhaps one of the most underappreciated aspects of the semiconductor revolution is the rise of brushless DC motors. Advances in digital logic, analog sensors, and power MOSFETs have all contributed to improvements in motor performance, size, weight, power, efficiency, and reliability. However, getting started with brushless DC motor design can still be very challenging. Thankfully, companies like Infineon have created brushless DC motor control evaluation kits and software that make this easier than ever. Welcome to Tech Chat, sponsored by Mouser Electronics, where we chat with engineering experts about the latest technical innovations that are shaping and reshaping our world. Today, we are pleased to welcome Peter Green to Tech Chat. Peter is a lead principal engineer applications at Infineon. Welcome to Tech Chat, Peter.
Oh, thanks, Dale. Thanks for having me.
So tell us about our topic of discussion for today.
All right, so today we're going to talk about a demo board that Infineon has developed for brushless DC motors, and it's designed around one of our new smart control ICs.
And there's no one better to introduce this evaluation board to us than Peter, since he wrote the book, or at least the product spec for this product. So Peter, let's dive right in.
Okay, so brushless DC motors are used in a wide variety of DIY and professional battery-powered tools, drills, saws, blowers, and these kind of tools. And also there's a wide variety of different motors in terms of voltage, size, torque, and other specifications. But in most cases, the brushless DC motors also include built-in Hall effect position sensors. And I'd like to also mention that brushless DC motors are used in robots and drones as well as in tools and in a lot of other applications.
Yeah, for someone who may be new to this topic, why have motors moved from brush to brushless designs?
Well, that's an interesting question. There are a number of reasons for that. Firstly, brushless motors can offer higher torque in a smaller form factor and don't have the problem of the brushes wearing down due to friction against the rotor. So in that case, the motor will eventually stop working when the brushes wear down. Doesn't happen with BLDC. And secondly, brushless motors produce less electromagnetic interference. So we've got the interference with radio and TV and other appliances to consider as well.
Okay, thanks for that explanation.
The motor drive inverter board is used in a battery-powered application to convert the DC voltage input to three-phase AC outputs, which control the motor speed. The board is designed around the Infineon 6 EDL7141 Smart Gate driver IC, which can be configured using motor control graphical user interface tool that we have. You can see here on the slide the lithium-ion battery pack, what a typical BLDC motor looks like, what our board there in the middle, the IC at the bottom, and then there's the motor control GUI on a PC there at the top.
So Peter, is the goal of this evaluation board to help designers both on the hardware side and the firmware allow them to shorten their design cycles and get some products to market more quickly?
Yes, we create evaluation boards so that the customers can test our ICs and our MOSFETs without having to design and build a board from scratch themselves. As you mentioned, this does shorten the design cycle, and then the customers can adapt our design to their own requirements.
And you mentioned earlier some DIY use of these motors. For somebody who's doing a small volume or one-off, they could probably just use the board directly in their design, couldn't they?
They could, in theory, but it's an evaluation board, so it's probably a bit big. It's probably not the right shape for what they would need.
Well, that makes sense. What are some of the key components and features of the motor drive board?
So the evaluation board shown here is designed around the 6EDL7141. Can work from 12 volts up to 24 volts. It's rated up to 500 watts. So we can get up to 25 amps RMS per phase. It uses the trapezoidal, or otherwise known as the six-step or block commutation method with Hall sensors. It has a switching frequency of 20 kilohertz. And basically the main components on it are a microcontroller, the smart gate driver, which is a three-phase gate driver, and our MOSFET power switches.
That was an interesting thing you said. So the trapezoidal, six-step, and block commutation, those are all just different names for the same type of motor control?
Yes, actually. There are several terms that are used. They're basically all describing the same thing. So it's six-step, it's trapezoidal, or it's block commutation. And these are pretty much interchangeable. So this is the most widely used control method for driving BLDC motors. There are some other control schemes, such as field-oriented control, but this is a more complicated scheme to implement.
Okay, thank you for that clarification.
So the 6EDL7141 operates in conjunction, as I said, with a microcontroller, in this case with the Infineon XMC 1400 series. It consists of a configurable three-phase half-bridge gate driver able to operate in multiple PWM modes with an integrated DC to DC synchronous buck converter and also a low dropout linear voltage regulator, as well as configurable precision current sense amplifiers.
Now, I know in this example here, you have Hall sensor inputs. Can this eval board also be used in a sensorless design? I know some people are using those today.
Well, we haven't actually tried it so far with this board, but it should be possible, although it would need different firmware because it would have to include some method of determining the motor's rotor position, probably from detecting the zero crossings of the back EMF voltages on the phases. So slide 6 is just showing the package, which is a QFN 48-pin power package with the bottom side thermal pad. The highly integrated nature of this smart gate driver IC allows a significant reduction of the component count and therefore reduction of the board size, which is very important because if you think about something like a drill, there isn't a whole lot of space to mount a circuit board and the components, so it has to be somehow packaged into a very tight space.
So this eval board has a number of Infineon products on it, but this one's kind of the star of the show. Is that fair to say?
Yeah, definitely. Yeah. So actually, this eval board was designed to kind of demonstrate this product. Yeah, as you say, it has other Infineon parts on it, but this is the one that's really the focus of it. The microcontroller communicates with the 6EDL7141 through an SPI interface, which enables the configuration and the monitoring. So the PWM signals are generated by the microcontroller, and these are connected to the gate driver IC, which provides the gate drive pulses to the MOSFETs. But these signals can be decoded in several different ways. So actually, the IC has some intelligence built into it. So you can set it, configure it to work in some different modes. So protection signals and current sense measurements are available also from the 6EDL7141 to connect to the microcontroller. So we have precision amplifiers which are connected to these phase shunts. Those signals are very small, they're only in terms of millivolts. So we need very precise amplifiers to increase the gain, the amplitude of those signals to a level where the microcontroller can then interpret and do an analog to digital conversion to be able to process that information. Also, the integrated buck regulator is a means of generating the onboard, let's say, housekeeping power supply that is needed to run all of the circuitry. So you imagine the gate drivers, the amplifiers, the microcontroller, all of these need a low voltage supply, but we have a battery voltage that could be anywhere between, let's say, 10 volts and 60 volts. So we need to have that onboard regulator to provide a supply to the rest of the circuitry. And additionally, there's also a linear regulator, so we can get a noise-free digital voltage bus for the sensitive digital circuitry that's on the board. And just one other point I'd like to mention is that we have built-in charge pumps to supply the high and low side gate drives, which means that we can have a duty cycle up to 100%. So we can cover the whole range of duty cycle.
So this really highlights what you said on the previous slide, that the chip contains a lot of the functionality all in a single package, and it's going to reduce the board size, because if you had separate op amps and separate gate drivers and the memory and the converters, that'd be a lot of hardware, and you've got that all packed into one chip now.
Yeah, I mean, that's absolutely right. That's the motivation for developing this part, really. We wanted to cut down on the number of components and really try to get all of it onto one IC so that we can save a lot of space on the board. The gate drive and hall sensor pulses sequences are shown here for the board operating with trapezoidal commutation, which, as we said, is also known as block commutation. The motor torque is controlled by the microcontroller firmware, which regulates the stator winding current through adjustment of the high side MOSFET gate drive duty cycle. The low side MOSFETs may be used synchronously or with body diode conduction. Hall sensors detect the rotor position and command the system to transfer drive to the next phase. This can be done via the microcontroller or alternatively by feeding the hall sensors directly to the 6EDL7141, which includes integrated hall sensor input comparators with configurable anti-glitch timers.
So I see the PWM signals on some of these, but then you got some blue bands on the low sides. What do those represent?
So this is just a way to try to show that it can be used in two different ways. So the low side MOSFETs can be off during that period where the blue bands are shown. The low side MOSFETs can be off throughout that whole period, in which case the commutation current will pass through the body diode. However, it's more efficient to use synchronous rectification, whereby the low side MOSFET would actually switch on during the period where the body diode conduction would otherwise occur. So when the high side's off, the low side is on. So what that's trying to represent there in the diagram is that it may be completely off, or it might be a series of pulses but out of phase with the signal that's above that one.
Okay, so you have options to the user how they want to run the motor.
Yeah, exactly, yeah. Here we see a set of waveforms captured from one of the phases in a typical system, in this case operating in synchronous mode. So you can see the waveforms down there, the pulses on the blue low side waveform. The phase current shows the characteristic trapezoidal shape, so that's that green current waveform. So in block commutation, it always follows that shape. It's a sort of 6-step type shape that you can see there.
Okay, yeah, so you can see here that it kind of has a trapezoidal shape, but then there's also kind of 6 unique steps in each cycle.
Yeah, absolutely, yeah.
That's very helpful to see why all the different names have come about.
Right, yeah. So the 6EDL supports several PWM modes which can be selected. This allows the designer a wide choice of microcontroller size and configuration options to cover a wide variety of different applications. So there are 4 examples shown here. So there's 1 PWM, 6 PWM, 3 PWM, and in the 1 and 3 PWM modes, the dead time can also be configured by this 6EDL7141, but in the 6 PWM mode, it's actually set by the microcontroller.
And then that dead time is important when you're turning the high side and the low side. You don't want them both on at the same time, correct?
Yeah, exactly. So you have to allow one side to switch off before the other one switches on to make sure we don't get any shoot-through currents.
Right, and being able to adjust that time allows you to drive a lot of different motors then.
It does, yeah. So, of course, as you say, different motors have different characteristics. So we might need a larger or a longer or shorter dead time, depending on that, and also how big the MOSFETs are.
Oh, yeah, that makes sense. How big is the capacitive load you need to drive to turn on that?
Exactly, yeah. Configurable gate driver allows the designer to eliminate diode resistor networks, which are commonly used in the gate drive circuits. So in most cases, gate resistors can be removed, therefore reducing the component count quite a lot and simplifying the circuit layout, allowing further optimization. So here, because we have a smart gate driver, we don't actually need any of these resistor diode networks, and we can connect the gate drive outputs directly to the MOSFETs.
So that's even expanding beyond, what you said before about all the complexity you pulled into the chip, but even how it functions means you can remove additional components from the system.
Yeah, and these are small components, but because you have so many of them, they take up a lot of space, and it really is nice to be able to get rid of a lot of that stuff.
Right. And like you said before, making it smaller means you can pack it in more tightly to some of these applications like a small drill, but it also improves the reliability because every component you put on a board is a reliability concern.
Yeah, absolutely. That's absolutely right. The high and low side gate drivers allow operation over the full duty cycle range up to 100%. The gate driver can be set to different levels, including 7 volts, 10 volts, 12 volts, and 15 volts. Because of the charge pumps, these voltage levels can be maintained even if the battery voltage drops to a lower level. And this allows standard gate drive MOSFETs to be used, meaning you don't have to use logic level parts. Control of the drain to source rise and fall times is actually one of the most important parameters for optimizing drive systems, affecting critical factors like switching losses, dead time optimization, and drain voltage ringing that can lead to possible MOSFET avalanching, as well as, of course, EMI optimization. So one of the key features of the 6 EDL7141 is the ability to control the rise and fall slew rates of the drain to source voltage by adjusting the gate drive sink and source currents during the different time segments of the switch on and switch off process. And this permits the designer to eliminate the diodes and resistors completely, and also to be able to optimize the EMI performance without actually having to change any components.
And that feeds into the discussion we were just having about able to drive different gate drivers by adjusting that current and the ramp rates.
Yeah. The 6 EDL7141 incorporates a complete system of power supply architecture, which I mentioned a little bit earlier, including the DC to DC buck converter. This can supply up to 300 milliamps, which is plenty to supply all the circuitry on board. The output from the buck regulator supplies the low dropout linear regulator as well, which can be configured to either 3.3 volts or 5 volts to supply the digital circuitry and the microcontroller. The linear regulator also has a built-in overcurrent short circuit protection, and it has a pre-warning function which can be communicated back to the microcontroller in case of a fault developing.
So explain to me how that pre-warning function works. What is it looking at?
It's monitoring the current, basically, and if the current goes too high, it triggers a kind of an alarm system that signals back to the micro.
Oh, instead of just doing a hard shutoff, it's trying to give you a warning and maybe the micro can do some kind of adjustment.
Yeah, so actually that's exactly right. So you don't want to switch it off immediately because then the micro wouldn't have any supply and the whole system would just die, basically. So it's to say, something's not right, but it allows it to continue working till it's able to shut itself down.
Well, that sounds like it'd be a much safer for these motor control applications.
Yeah, I think so, because you never know what kind of fault condition might be causing that to happen, and there might be some safety consideration.
Exactly right.
The three-phase gate driver section of the 6 EDL7141 is supplied by charge pumps. Each charge pump uses an external switch capacitor to transfer charge from the buck converter output to the gate driver bias supplies. The low side is referenced to 0, but the high side is referenced to the system positive supply rail. So, and that one is actually able to supply all 3 of the phases. So the values of the switch capacitors and the bias supply capacitors must be selected correctly according to the datasheet instructions in order for those charge pumps to work correctly. Also, the clock frequency for the charge pumps can be selected between different values, and there's even a frequency modulation scheme built into that, which spreads the EMI so it doesn't generate these high peaks at a specific frequency that might go over the limit on EMI.
And I would imagine the modulation is at such a high frequency that it doesn't even show up at the output of the system.
No, you wouldn't notice it at the output of the system at all, but it's just, when you're doing the radiated EMI, you sometimes get a peak that occurs at a certain point. And if you can spread that rather than have it all concentrated at one frequency, it's an advantage.
Yeah, and passing EMI in a lot of those tests that you have to do to sell these products, that's a big deal because you're moving a lot of current around on these boards.
Yeah, that's right. As I mentioned earlier, there are also 3 precision current sense amplifiers. These can be used for different types of designs with 1, 2, or 3 shunts. The amplifiers have various options that can be configured. The gain and the offset are also configured internally and can be set via the user interface. An additional output buffer allows adding a variable offset voltage to the sensed amplifier output, which can be set to 4 different values, either by programming the internally generated level or applying an external voltage. And there's a pin available to do that. So with this implementation, negative current can also be measured. So we have a positive overcurrent comparator to detect an overcurrent condition. And this can be used to do a kind of cycle-by-cycle current limiting on the phase outputs. There's also a negative overcurrent comparator to detect a negative going overcurrent condition. So it's sort of a smart fault detection system.
Is there anything on the chip that isn't configurable? Because it seems like everything you talk about can be configured.
Well, that's a great question because we have over 50 configurable parameters on the IC. I'm sure there's 1 or 2 things that can't be configured, but we've tried to make it as configurable as possible.
I see that. Well, that's going to be great news for all the designers out there.
Exactly, yeah. So when triggered, the 6EDL7141 can apply different braking modes to stop the motor. So braking may be externally commanded via an input pin or automatically triggered by a fault condition such as overcurrent or some other fault condition. The desired braking mode can be selected from several available options, including high side braking, low side braking, or alternately switched high and low side braking. Or we can just switch all of the MOSFETs off together.
Why all the different types of braking?
It's really because different customers have different ways that they like to do it, and it might be that a certain design may require it one way, but another design may want to do it a different way. So we're just trying to offer as many different alternatives and options as possible.
Because you can configure that as well.
Yeah, absolutely. So the GUI tool enables the system designer to configure the 6EDL7141 parameters from a computer and also control the motor speed and monitor the system. So you can control all the parameters, but you can actually run the board from this GUI as well, and it will read back the speed and you can adjust it. You don't have to use the GUI to do that, of course, but you can. It has all these different possibilities. And it's just connected to the board through a USB cable because the board has an onboard debugger. So if you had a motor drive without an onboard debugger, you would need to have a separate small debugger board, which is also available. So once the desired values for whatever the parameters are have been selected, they can be transferred to the board using this write device option. In this case, the values are held in a volatile memory and can be changed. Even while the system is running, you can tweak a parameter until the system performance has been optimized. When the designer is satisfied that the optimal set of parameters has been determined, they can burn these values into the 6EDL7141 one-time programmable permanent memory. But after that, you can't make any more changes. So the GUI offers a convenient and easy-to-use tool for bench verification of any design based on this IC.
And that GUI is available for free download on your website?
Yes, absolutely. Free to all the customers. So slide 18 is a summary of the system benefits. So we're looking at it's highly integrated, so we have a significant reduction in the size and component count. It's robust. It can operate from a wide battery input range from 5 volts up to 60 volts. It's very flexible, so we've got configurable gate drive to allow system optimization through the PC-based GUI, reducing the design process and enable faster time to market. We have EMI compliance. So again, the adjustable gate drive sync and source currents allow the designer to adjust the slew rate, which determines the amount of EMI that's going to be radiated by the system. So if they're at a lab doing the testing, then it's just going over the limits, they can adjust the parameters so that it will pass the EMI test. So programmability, we have more than 50 programmable parameters, including PWM modes, buck converter frequency, current sense gain, protection modes, braking modes. And we also have, under the protection modes, we've got under voltage, over current, rotor lock, and external braking. So that's a summary of the benefits of using that 6EDL7141. And there is also a web page specifically for this evaluation board where the link is shown here.
And for designers that complete their development using this eval board, do you also provide like the bill of materials, schematics, and layout files to help them get started toward a custom design?
Yes, definitely. On Infineon's website, we have a dedicated page, as I said, for this board. And from that page, you can download all of the design files, the layout files, bill of materials, everything that goes with that board.
Well, thank you, Peter. Before we sign off, I want to encourage everyone to check out all the latest Infineon products at Mouser Electronics, our sponsor for today's Tech Chat. And a special thanks to engineer Peter Green from Infineon. Finally, please join us again next time on Tech Chat, where we chat with the leading technical experts like Peter Green from Infineon, who are changing our world every day. Thanks, Peter.
Thanks, Dale. Nice talking to you.
You too.